I've been sent another maximization or minimization problem, and this seemed to be an interesting twist on what we've already done. So let's do this one. Let's see. A rectangular storage container with an open top is to have a volume of 10 meters cubed. The length of its base is twice its width. So let me start drawing this thing. It's a rectangular storage container with an open top. So let's see. Let me do it in a different color. Let me do it in this color. Okay, so I'll do it over here. So that's its base. So let's see. The length of its base is twice its width. So if this is the base, and if I call this the width, so this is x, the length is twice that. This is 2x. Right? The length of its base is twice the width, right? So this is the length of the base. This is the width. Okay? Material, and then the height. The height, for now, is unknown. But I think we should be able to find a constraint on this because we know what the volume has to be, right? It says material for the sides costs $6 per square meter. Find the cost of materials for the cheapest such container. Okay, so let's do a couple of things. First, let's figure out what the height is in terms of x. And then we can find an equation for the cost in terms of x, and then take the derivatives and find the minimum, etc., etc. So what do we know about this? What's the volume of this box? The volume of this box is equal to the, what is it? What did I say this? This is the length, but it doesn't really matter. Length times the width times the height. So it's 2x times x, 2x squared times h. So it's 2x squared times h, right? Base times height times width, or whatever. Length times width times height. Just the volume of a rectangle. And they already said that the volume is 10 meters cubed. So that gives us a good constraint. So that has to equal 10. Right? Let's divide both sides by 2x squared. And so what do we get? If we take this equation, we divide both sides by 2x squared, we get h is equal to 10 over 2x squared, which is equal to, we could say 5x to the minus 2 power. So we could write this as 5x to the minus 2 power. That is h. We have just solved that. We were able to solve that because they gave us a constraint on the volume of the box. Fair enough. So now let's see what the cost of the material, the total cost of the material is going to be. So I'll do that in magenta. The cost of the material, and I could even say as a function of x, is equal to what? Okay. Material for the sides cost $6 per square meter. So what is the surface area of the sides? Oh, no, they tell us the material for the base first. So material for the base costs $10 per square meter. So this base right here, the material costs $10 per square meter. So what is the cost of the base? Well, it's going to be the area of the base times 10. So it's 10 times the area of the base. What's the area of the base? It's 2x times x. So it's 2x squared. So this is the cost of the material on the base. And now we want to add the cost of the material on the sides. So, and this is where it gets a little bit interesting. So there's two sides that are x. This side and this side are the same size, right? And so what are they? What are their areas? So it's going to be $6 per square meter for those two sides, right? For this green side, and that one back there as well. I don't want to make this too messy. So it's $6, and what's the area? And there's two of these sides, so I'm going to multiply by 2. And so what's the area of each of these sides? It's x times 5x minus 2. So that's 5x minus 1. All right, so now we have to figure out this side here and that side over there. And let me do it in a brown maybe. So now we care about this side up in front and then that side back there. But that's also going to cost $6, right? So plus $6 per square meter. And then there's two sides. And then what is it? It's 2x times 5x to the negative 2. So that's 10, right? 2 times 5 is 10. X times x to the negative 2. X to the negative 1. So let's simplify this. So we have the cost, and there's no root. It said it was an open top, so there's no fabric we need for the top. So the cost of putting the fabric or the material on this open rectangle is, see, 20x squared plus, what's this? 12 times 5 is 60. X to the minus 1 plus, let's see, 12 times 10, 120 x to the minus 1. And so we can further simplify that as 20x squared plus 180 x to the minus 1 power. And now we're ready to just take the derivative and find out what the minimum point is of this curve. So let's do that. So c prime of x, and this is a fun non-hairy derivative. So it's 40, right, 2 times 20 x, and then minus 180 x to the minus 2. And the minimum or maximum point are going to be where this is equal to 0. So let's set that equal to 0. Let me clear up some space. I think you understand all of this. So let me get rid of that. Okay, so I need that tool. Okay, actually I like the drawing, but it's got to go because I need the room. If you need to review it, just rewind the video. Okay, so we want to set the derivative to find a minimum or maximum point. At minimum or maximum points of the curve, the slope is 0. So the derivative is 0. So let's figure that out. So 40x minus 180 x to the minus 2 is equal to 0. I don't know. The first thing I would do is just you could divide both sides by 20, and you get 2x minus 9x to the minus 2 is equal to 0 divided by 20, which is 0. And then let's see what you get. If you add 9x to the minus 2 to both sides, you get 2x is equal to 9x to the minus 2, or 9 over x squared, right? That's the same thing as 9x to the minus 2. Now, I don't know, let's multiply both sides of this equation by x squared. And so you get 2x to the third is equal to 9, or x to the third is equal to 9 halves, or x is equal to the cube root, or we could just say 9 halves to the 1/3 power, whatever that could be. It's 4.5 to the 1/3 power. And do we know that this is a minimum or a maximum point? Well, we could go and take the second derivative and then confirm that we're concave upwards at this point, and then we would know that we are at a minimum point, and this is the cheapest such container. But I'll tell you a little, if you see this in a class, and maybe you want to prove that for yourself on a test. But an easy way to test that is just try some other x, right? We have the cost function right here. Try some other x, and you know that this is either going to be a maximum or a minimum, or at least a local maximum or minimum. And if you try another x, and if it's greater than, this is a minimum. Or the other thing is, well, if there's only one critical point, and they asked you to find the cheapest container, that critical point is probably going to be the minimum point. But anyway, so just for fun, let's figure out what that is actually equal to. I'll actually go to google.com, and let's see, Google, and we could just say, what do we want? 9 halves to the 1/3 power. So that is 4.5 to the 1 divided by 1/3 power. 1.65. So that's our answer. If x is equal to 1.65, so, plus some other points, then we have the cheapest container to produce. So it's 1.65 something something. And there you have it. Hopefully you found that vaguely useful.